well, we still have, what, another month or so in the term where we can avail ourselves of this 10-minute cushion on things, and we'll all have to learn to be much more punctual. My name's John DeChico. I'm a research professor at the Energy Institute, and the Energy Institute, in collaboration with the School of Environment and Sustainability and the Herb Institute for Sustainable Enterprise, are really honored to have been awardees of one of the distinguished faculty and student seminar series over the past 2 years. This talk is as part of that series, which we've entitled Climate Mitigation, Moving Beyond Carbon Neutral. Today, it's my really double pleasure, in addition to often introducing some of these talks, to introduce Rob Socolow, who I knew of when I was doing a master's degree at NC State and working on the North Carolina State Solar House project. I was one of these childs of the energy crisis, and was very motivated to get into solar energy, renewable energy at that time, and had a great master's thesis project doing the first year evaluation of a solar house demonstration project on the North Carolina State University campus in Raleigh. And as part of my literature research reading, I came across the work that Rob and his team were doing at Princeton, and I came across the book that he was the lead editor of at that time in the late 70s, called Saving Energy in the Home. And that book was an incredible eye-opener for me in terms of the power of empirical work to really not just offer insights into diagnosing problems, but also into really identifying solutions that often might be right under our noses, but until we really measure things and understand them, we might not see. And then I was, a few years later, lucky enough to have the privilege of going through the doctoral program with Rob as my advisor. Many of you know him probably through a number of his other guises and contributions over the years. Probably a lot of people know the stabilization wedges paper. I guess that was, what, 2004? Yes, that Rob co-authored with Steve Pacala. He's done a lot of work on conceptualizing, committed emissions, high emitters, and now more recently looking at density studies. And he still remains very engaged in multidisciplinary efforts to anticipate key issues surrounding low carbon futures. In terms of his credentials, Rob's now a professor emeritus of the Mechanical and Aerospace Engineering Department at Princeton University, and has many honorifics: American Academy of Arts and Sciences, National Research Council Associate, Fellow of the American Physical Society, as well as AAAS, and a recipient of the Leo Szilard Lectureship Award by APS. Rob got his doctorate from Harvard in theoretical high energy physics. Is one of the originals, in the sense of a generation of physicists trained in, say, high energy physics or particle physics who were motivated to begin looking at applied energy work, and he, began doing that work. I know you led the Center for Energy and Environmental Studies, and as that got absorbed into Princeton Environmental Institute, and Rob's been working on this stuff for decades and continues to have a lot of energy and a lot of insight, which he'll now share with you.
Thank you very much. It's a treat to be invited by a former student. I'm hard to resist. And I had a marvelous day with some profound conversations about the energy problem. How close do I need to be to this to make it work? Does that make a difference coming this close? It's a small room, but I also know they're recording the talk, so I'll try to do both. So this is an important slide for me, and I hope for some of you. A mentor of mine, after I left physics, inspiring me that I could do something in sort of social physics, was your own Mark Ross, who died last year. And there was a group of us, as John alluded to, who, in the excitement of the 60s, science for the people, already being at the assistant professor level or something like that in physics, moved out. And he's the one person who was a step ahead of us. John mentioned Art Rosenfeld, who may have been the second most famous of us. I led him out. Another one who went independently but inspired by Mark was John Holdren, who was the president's science advisor under the 8 years of Obama just now. So we were a group that somehow felt we were encouraged to believe and reinforced each other's beliefs that we could make a difference using physics as a way of getting into social problems. Mark, as I say here, was selfless, cheerful, calm, deliberate, and incredibly creative, opening up one area after another. He's also the fellow who brought John DeCicco here before, in his later years, or at least John came here because Mark was there. That made it a little bit more accurate. I would like to see, I'm lobbying now, at least one, but preferably 2 or 3 ways of memorializing John on this campus. Some of those can be fairly easy to do. A seminar series, fellowships named after him. It takes some hustle, it probably takes some contributions. Maybe someone out there is well-heeled enough to put some money behind something like this, but it can be done at no cost if it has to be. So I hope that will happen by a year from now. It's my challenge to you. Everybody I've said it to in the day since I arrived has been saying, that's a good idea. So I was part of a study, which is kind of why you invited me for this particular series. Produced this book in 2011, after a 3-year process. Again, through the physics community, the idea, actually I'm responsible for what's happening in the physics community. There is at the Physical Society a panel on public affairs, POPA, which was invented in the 70s along with everything else that was happening, which was represented by science activism. And it's a standing committee, and it does studies. And I suggested this topic because colleagues of mine had gotten interested in it, and I thought it deserved more attention than it was getting. And so we put some points on the board in the study of the subject of this seminar series, negative carbon, by a rather detailed science-based evaluation of this option. The committee is in front of you. Some of these people are very distinguished. 3 of them had industry backgrounds, and when it came to costing, it was kind of their show. All 3 of them, one at Tennessee Eastman, one at BP, and one at Alstom, had the job for 30 years maybe by that point of taking the harebrained idea of some member of their company that wanted them to invest, wanted the board to invest in some project, and figuring out what kind of economics it had, sometimes encouraging it, sometimes saying no. And so they took this problem on as another thing that they should put a price on with their methodologies. I'll say more about that. I had 3 co-chairs, and the story of this study intersected with the early years of the Department of Energy under Obama. Bill Brinkman, who became senior under Steve Chu, started the project with me. He, more than I, got the yes answers from the committee we recruited, because he had been running the Bell Labs science program in its heyday, and he was very well known. He'd been head of the American Physical Society. We got almost 100% yeses when we put the committee together. Then Obama and Steve Chu called him to Washington, and Arun Majumdar stepped in, who was already on the committee. And then he became head of ARPA-E just a few months later. And so we were down to co-chair number 3, who is a terrific guy, Michael Desmond, who was one of the 3 industry people, chief chemist at that time at BP. Some of you know various names there. I'm not going to go through them. This is in terms of placing this within the context of this seminar series, Direct air capture, I think I actually was the person who coined the name. We didn't have a name for pulling CO2 out of the air with chemicals. And as opposed to all the biological names or biological concepts. And I think at one point, I may be wrong about this, but I wrote down, started calling it direct air capture DAC for the purpose of our report. But putting it here alongside a number of the other strategies to do the same thing. Take CO2 directly out of the air. Because there's too much in it, we want less in it. I mean, when you sell it to people, we got a problem with CO2 in the air, let's just take it out. Laymen get to that answer a lot faster than people with technical backgrounds. So there's a lot of biological strategies, and there are non-biological chemical strategies other than the one that we're mentioning here. I've got a word there, pickling. Well, the biological, biopowered CCS is the favorite of the IPCC community, in which you grow things, you put them into boilers or gasify them, put them in gas turbines, you make electricity, you trap the CO2 instead of letting it go to the atmosphere, you put it below ground. CO2 has come into the plant by way of photosynthesis, vegetation by way of photosynthesis, into the power plant below ground. You're scrubbing the atmosphere. If you don't make electricity at all, this is not a popular one, but it makes a certain amount of sense. Grow something and put it below ground, intact and evolved, or deep underground, or drop it into the sea. Ships have been pulled out from the sea. 100 years later, there's something called the Vasa in Stockholm, which was pulled out of the sea 300 years after it fell down there. It sank in its maiden voyage, if I remember correctly. And so it wasn't weighted properly. And all the wood was there. So you can pickle and that's another strategy. Soil carbon augmentation is a favorite from people now. We have depleted this, wherever we have agriculture, we pretty much reduced the carbon in the soil by a substantial amount in the first meter or so. Plowing it over and over again, aerating it. The carbon that was deeply irreducible is called recalcitrant. And put it back over strategies including not plowing the land, but other things you might do, and just put it back. Substantial, significant amounts of carbon go back that way. So the list is long. Our system, we wanted to put a cost on a carbon, an example of this. We picked a system close to what is being done by one of the current investigators. I should say there are a few projects out there right now, typically privately funded, and they were out there when we wrote our report. They've gone further, and only one of them uses what people deliberately shows a conservative strategy using well-known materials. You basically blow air over sodium hydroxide, form sodium carbonate, and with some subsequent steps, you regenerate the sodium hydroxide, and you have concentrated carbon dioxide, which you do something with. And the work of taking it out of the air is essentially right now decoupled with doing anything with it. So that would be, but we feel as if we know what to do with carbon. At least we can put carbon dioxide once it's concentrated below ground. So there is in the process, you need that particular system to get back the sodium hydroxide requires a high temperature furnace and essentially the cement industry's kiln. And we put this all together and we came up with a cost. It's David Keith working in Canada on his demonstrations, who is doing something in this general class of projects. Klaus Lackner doing a very different thing I'll mention in a moment. Looking at our work, thought it was a marvelous comment, said, you'll studied a penguin to see if a bird could fly. The view being that we put a price on something, so obviously not the best idea, that nobody should take our costs too seriously, because people will have much better ideas before long. One hopes so. There isn't a clear new idea that is going to sweep the boards, but that is not a silly comment about our project. And I want to just say quickly, because our number, which is $600 a ton of CO2, has a lot of things in it. It's a very high number. It made my previous friends unhappy with us for having such a high number, but we did it by a methodology that was essentially driven by industry cost makers, asking about doing it now for the first time, not doing something after you've been at it for 20 years. What they would tell management it would cost to do with their methodologies. And then to help understand what their methodologies were, they used the same methodology to look at a coal power plant's CO2 removal. By that point, the National Energy Technology Lab already had done calculations like that. Okay, so let me take it from there. Basically, our number was in the $600 a ton of CO2 range, with a factor of 10 higher than flue gas separation. The concentration ratio is 300 between a 12% CO2 in a flue gas of a coal plant and the CO2 in this air at the moment. Of course, ours is going up because we're all breathing in this room. It might be a little higher before the seminar is over. R&D will bring it down, and I deliberately made a longer arrow for the R&D of air capture than the green arrows than the R&D of a mature industry like CO2 capture from flue gas. And we had a hard time getting our program out of the American Physical Society's review process, really the POPA review process. Once it got through there, the higher level APS review process was not so onerous. But a lot of physicists thought this is so absurd that APS shouldn't be associated with it. That's only 2011. And then if we were going to say something, it shouldn't be a number as low as $600. So we were pushed up and we resisted. We said that people did this process with their own methodology. They believe the number should be there. I refused to let the number go higher in order to get it out. In point of fact, I added a column under pressure that got to 800. The other investigators right now are using a solid instead of liquids. The previous idea was to blow it over sodium hydroxide. It's actually sodium hydroxide as the liquid is dripping over a baffle and packing material while the CO2 is blowing past it, either crosswise or countercurrent. So it was a liquid strategy we were looking at. All the others are using essentially materials that are not familiar, not produced in industrial quantities at this time. And we did that, my team did that calculation and came up with a price higher than $600 for this alternative mechanism. And I said one high number is enough. Let's explain the principle, the number one, the driving calculation, just put it really simply, and then indicate that unlike the other one, we had nothing really to anchor a calculation. So it's the cost of the sorbent. Now, the material that you can't buy today, it's going to be exotic in some ways. What will it cost when it's produced in bulk? And how many cycles will it last? What you're talking about here now is that something absorbs CO2. It then goes in one space, in one industrial environment, is brought to a second space. Maybe it's as much as just changing the pressure or the temperature in the same space, but it's a different space. It may physically move, and then it's regenerated, and it goes back to the first one and does it over again. So it's a cycle, in and out, up and down, and left and right, whatever. And so they revert how much it takes out of the air per kilogram of itself in a swing, as it's called, is one measure. Kilograms of CO2 absorbed or desorbed per swing, or per kilogram of sorbent. How many cycles before you have to take it away and buy new stuff and put it in, and the cost per kilogram. And those three numbers really are not pinned down much. There's a study going on right now about to release this report on the subject of this whole series by the National Academy of Sciences, and its chair is my strong colleague, Steve Pacala. And he's telling me that they get a factor of 1,000 range of this number by this calculation because each of these things is not pinned down. Like Nate Lewis on our committee called this search a search for non-obtainium. An element that it's got a fractional number and somewhere in the periodic table. But people have got ideas, and that calculation is probably the one that will show that there's a better strategy around sorbents of some kind or another than the kind of strategy we did. But David Keith is saying, no, those will always be difficult. The kind of way the direct route I'm taking, brute force, will be better. So that's one of the interesting comments. Just putting three numbers in there to see how the multiplication goes. 50 grams of CO2 per kilogram of sorbent, 4,000 swings and $10 a kilogram. I think at the time, numbers like that were regarded by the people who knew much more than I did as plausible. Gave you a $50 a ton of CO2 contribution from that term alone. And so I wanted to, now you're educated to do any calculation that anybody asks you to do. This is all there is to it. The big cost is building something. I don't have a slide on that, do I? When you think about the cost of this, let me just see where we are. Just 1 second. Yeah, I'm gonna insert something here because I took it out later. The other calculation, how big is that? What bothered the physicists so much about studying the subject? A back of the envelope calculation of how much air you have to intercept, because CO2 is 400 parts per million. And I carry around a single mnemonic that lets me scale up other things. The average American emits about 20 tons of CO2 a year. If I have a 1 meter square object, think of a portable house fan, and I pull air through it continuously at 2 meters a second, and I take out half of the CO2 that is in the air, so it comes out at 200 parts per million on the other side, I have countered my 20 tons a year. So that's a rule of, because the calculation involves moles and air concentration, all sorts of simple numbers to look up, but I memorized the back end. So if you've got 6 million tons of CO2 per year coming out of a coal power plant, that's 300,000 times 20, and so I need 300,000 square meters of frontal area. If I make that thing 10 meters high, I've got 30 kilometers of wall, 10 meters high, that the air must blow through. So that's a very big structure, whether you break it.
Put
Now,
it next to Mexico.
you put it in New Mexico and we're gonna make real progress. That's a very interesting suggestion. Very interesting suggestion. So you get a sense of this enormous area that has to be there. You can't really walk away from it. Some of the suggestions do things at a modular scale where you're taking a ton a day. That's Lackner's favorite number. So 300 tons a year. And then you're going to have lots and millions of them. But you have to have the area somehow. Now, in doing the cost calculation, there's an important consideration. This goes across, the next things I'm going to say apply to all the negative carbon ideas. There's energy required to make them happen. And where is that energy coming from? No obvious answer. Clear, this issue will depend on where you put it. But it is not hard to imagine, at least, that you would put more than one CO2 into the atmosphere for each one you took out, because it was an energy-intensive process and used carbon-intensive energy. So looming over this process is that this could be worse than nothing. Putting it in mathematical terms, there is a factor of 1 over 1 minus x, multiplying the answer. 1 over 1 minus x looks like that curve. It goes to infinity at x equals 1. And it means that it is telling you if it's x is a half, that you're going to put 1/2 molecule in for every molecule you take out, so you have to do twice as much work to get the same thing out as before. And what is x? It depends on how carbon intensive the energy is. So use renewable energy to do it and you won't have any problem. You'll get x waste to be very small. What's the problem with using renewable energy to do this? Any? There's something called an opportunity cost. that same renewable energy, if there's still a coal power plant running somewhere, could have run instead of using the coal power plant, closed it down. So this 1/1 minus x issue is subtle, important, and to my mind establishes a sequence that the fossil energy, the assignment of reducing the carbon intensity of the global economy, or pretty much global economy, much of this is fungible from one place to the next, it is a prior assignment to getting the carbon dioxide out of the air, to the extent that you can't get away with minimal carbon energy inputs into getting to make this work. And this applies across, and the energy input, people don't like to talk about the tractor or something that's going to spread a mineral out over the ground and then vacuum it up again. Each of those is an energy intensive step. And you have to be careful. The biofuels in the US as carbon strategies are vulnerable. The corn ethanol program is the one of everybody. It's going to help. It's going to sound very strange in the recording because I keep stopping and starting. I'm sorry for the whoever has to listen to this. I apologize. Where was I going a moment ago? Everybody who doesn't like a technology tells people like me that they know that this same argument applies to it. The nuclear people will explain about all the energy to make a PV cell. And the PV cell people will tell me all the energy it takes to enrich uranium. It's a guaranteed weapon in the conversation. In general, those calculations are not that nasty. And the answer is, of course, there is some energy use, but it isn't making the technology silly. The one which I think is closest to making it silly is the biofuels program, because there's just lots of energy inputs all the way through it. At least the numbers that I've seen that come out of that represent like x equals 0.8 to 1.2. And so you have not got it. You may have a national security argument, but you don't have a great carbon argument. But again, I may be out of date. They may have reduced these numbers. Sugarcane is better than corn by a lot in the overall story. But watch out for it. Another subtlety of the calculation of this, the attractiveness of any of these, I'm putting CO2 in the atmosphere today. How much stays there? Do you all know the answer to how much stays there if you put carbon dioxide in the atmosphere today? I'm putting 40 billion tons of CO2 a year into the atmosphere by burning fossil fuels. How fast is the atmosphere concentration rising? Anybody know the fraction you multiply the 40 by? It's about a half. So roughly we're putting 2 carbon dioxide molecules into the atmosphere, and between the land and the ocean they're taking 1 out. So now I'm going to take carbon dioxide out of the atmosphere. Will all the arrows reverse? Well, they might. The ocean will outgas. On the surface, it's an equilibrium between the surface ocean and the atmosphere. If you take it out of one, it will go into the other. And put it into one, to go into the other. Forests are fertilized by CO2. If I take the CO2 out, there should be defertilization of some sort. Leaves. It seems more complicated than that, because there are some, and it's not obvious that this is as strong a factor of 2 as strong as a factor of 2, because, for example, the deep ocean and the surface ocean both play a role in determining how much CO2 goes into the ocean. And the deep ocean will keep coming to the top, and it last saw the atmosphere 1,000 years ago, so it thinks the atmosphere doesn't have much CO2, it doesn't have extra CO2 in the first place. And as long as it finds that kind of CO2, that kind of atmosphere that's higher than it was, it'll outgas CO2. I'm sorry, it'll absorb CO2. So the deep ocean is still working to take CO2 out while the shallow ocean is giving it back. And so you have a more complicated calculation. Something like that goes on with wood and leaves as well. But we don't have a good answer. But it's going to push the number up that you have to do, the size of the job. The third thing is, how fast can you put CO2? How fast can you take CO2 out of the atmosphere? What kind of strategy is this in the framework of climate emergencies? So I have 2 arrows here, both of which have the goal of lowering the atmosphere by 100 parts per million. It's now 400 parts per million, the atmospheric CO2, over 100 years versus 10 years. And they both have that area, because that's the job that's done, equal, and have not allowed for any multiplier for the outgassing of the ocean. Just take the straight CO2. So it's a lower estimate. And those two slopes are a factor of 100 different, because the rise is 10 times less than the rise over the, what's the other word? So there's a factor of 100 pace difference. And I think you can persuade yourself that a credible enterprise would grow in curve A, so that in 2070, we really could decide that we had 100 ppm more in the atmosphere than we wanted. And we committed ourselves to a 100-year program as a world, so that we got it down from, say, 550 to 450 in that century of activity. If you say we can do it in a decade, you're talking about essentially replacing the entire compensating the entire fossil system every 2 years, 5 times in that decade. That is extremely fast. So in my mind, it's an important difference between carbon dioxide removal, CDR, and what's called solar radiation management, which is the other kind of geoengineering that people are discussing at the present time. The biggest difference is that can act. A very big difference is that one can act quickly and one cannot act quickly. They are different also in that this carbon dioxide removal strategy really is global. Quickly after you take the CO2 out, it's homogenized around the planet as to how much less it is. Where solar radiation management, which is reducing incoming sunlight, probably can target certain areas like the Arctic. It's thought of as a global strategy. It has the opportunity probably to be differential. And carbon dioxide removal, it's hard to see how it leads to enormous trouble. It's kind of okay. Nothing terrific about it, nothing really dangerous about it. Solar radiation management means modifying the entire planet, it's doing experiments with it. It's hard to make the experiments. There's a lot you can do on the front end to get some idea of the problem, but the question of whether there's any experiment you can do that's small enough that you can reverse the effect, but large enough that you can see the effect. So it's a very different domain, which is why people have tried to separate the two from each other. It leads me to an overall view of this problem that it's kind of not that important to do it now. There's nothing wrong with doing it, except to the extent that it diverts attention. An R&D program won't hurt anybody. There may be spillover, but whether you're talking about biological or industrial versions of this, and I know that's been the whole subject of your series. It's the flavor of the decade. Lots of scientists are trying to do this as well as turn CO2 into usable materials. And as I'll say in the next part of my talk, which is coming in a moment, it depends a lot on where you think we are in solving the climate problem. If we're nearly done, we've got the renewable technologies, we can get on with the job, then we have to do it we have to do some of the last mopping up. Then it's really there. If we're not even really underway, if we haven't made the sale, and I'll talk about what that means, then it's partially, as I say, harmless, partially a distraction, getting an early view of what will be necessary later. But I do worry that we're putting too much, that we're putting too much attention to it. It's not going to be that cheap. This net carbon argument is stated there. In the long term, it does compensate for the hard to remove CO2 emissions from vehicles, and suggest, for example, airplanes. If you don't think we'll have an electric airplane or a battery airplane, you can do it with biofuels, you could do it with some of these things. And if you're going to do a lot of it, I think this direct air capture, now differentiating among CDR strategies, the direct air capture, which is not land intensive, is a better choice than trying to grow lots and lots of stuff and put it through turbines as vegetation and capture the CO2. It's incredibly land intensive. You're talking about hundreds of millions of tons, hundreds of millions of hectares. And the enthusiasm for that in certain circles bothers me. finally, on this, we have an obligation not to oversell this, to the extent that because people want to believe that it is an available, low-cost strategy. And then you can somehow feel happier going to bed at night and so on, that this thing is going to be a big deal. It's really important not to create false hopes that allow our audiences to infer that humanity can solve climate change while being relaxed about fossil fuels. John's encouragement, I'm going to put part 2, which is a talk that I've been developing, which is meant really about the context. And I'm going to start with a quiz. There's actually a book out there, because I've been using this quiz a long time, and it's called Socolow's Quiz in One Book. You have to put yourselves in one of these 4 quadrants. And you take a minute to say, you have to answer 2 yes and no questions. Are fossil fuels hard to displace, and is climate change an urgent matter? So take a minute, decide which quadrant you're in, and I'm going to ask you to raise your hand when I go across the 4 quadrants. Ready? Who's in the top left? Nobody in this room. Who's in the top right? Climate change is not an urgent matter, and fossil fuels are hard to displace. Nobody in this room. Does anybody think there would be no audience in which there would be people who'd be in that box? We'll talk about it in a minute. Whoops, sorry. Who's in the bottom left? Quite a few people, quite a few people. Fossil fuels are not hard to displace, and climate change is an urgent matter. And who's in the bottom right? More of you. I'm in the bottom right. I respect people in the bottom left. I've tried to put a name on the very kinds of views of the world that we're talking about. There are people, certainly in my early education, when I was surrounded by nuclear scientists who were not, and we'd hardly thought about climate change. We believed nuclear too cheap to meter, coal industry was done for, we would have nuclear power plants doing the job, we'd have a no, fossil fuels are not hard to displace, and climate change is not an urgent matter. Top right, where none of you were, I would claim a lot of people in the fossil energy industries and people who rely on them, and lots of others who generally have, they certainly believe that they're hard to displace, but they also tend to think climate change is not an urgent matter. I'll say why. In bottom left, where many of you were, the fossil fuels are not really that hard to displace, but climate change is urgent. The top left and the top right and the bottom left, the off-diagonal elements in the math language, are the ones which protect you from the psychologist's concept of cognitive dissonance. They work together, they let you go to sleep, they let you sleep well. And the bottom right is a nasty place to be, where you have, another way of saying this was the children's game, what happens when the irresistible force meets an immovable object? I think there's even a song by it. I remember being teased by that about age 10. What happens when the irresistible force encounters an immovable object? Any of you like that? I mean, I think it's kind of fun. That's the sort of paradox that kids get into when they're beginning to ask about the world. I'm interested that so many of you are on the bottom left. It's a different, I would say that to the extent that you're on the bottom left, carbon dioxide removal is a plausible priority, because we have nothing in the way of getting on with the rest of the job. To the extent that you're in the bottom right, it looks more like a luxury. And so I think that I've sort of been digging away at this, particularly getting ready for this talk. I would put temperatures on these 3 things: global rise of average surface temperature, that the 2 degrees target that is in front of the world thanks to the Paris Agreement is essentially a bottom left target. The relax and enjoy the fossil fuel world, nothing's going to happen anyway, top right target is a 5-degree target, meaning that the world is going to keep sailing past the targets we're talking about and essentially not do much about fossil fuels over the next 100 years, or at least say 50 years. And the bottom right target is you work like very, very hard, because it's difficult to get the fossil fuels out, and you succeed through invention, policy, world becomes enough alarmed, the problem is taken on, and you end up at something like 3 degrees. So putting those numbers into some context, what is a temperature, how does the temperature relate to a fossil fuel level of effort? There was a kind of simplification of this whole subject a few years ago when people said, we can make a first approximation that not fossil emissions at any given time, but the integral, the total fossil fuel emissions ever is proportional to the temperature rise on the planet long term. It doesn't matter when it goes in, doesn't matter where it goes in. And that the multiplier is approximately 1,600 billion tons of CO2. I'll help you get your arms around that number. Will give you a 1 degree Celsius rise in the average surface temperature of the planet, usually anchored to the pre-industrial concentration of, say, the 18th century. The temperature is about 1 degree Celsius higher now, and emissions of fossil fuels since the beginning of the fossil fuel era is about 1,600 billion tons. So those numbers roughly match. What am I leaving out? I'm leaving out land use change. I'm leaving out non-greenhouse gases other than CO2. Only physicists can, with a straight face, do as much hand waving as I'm doing right now, but it's our stock and trade. That means that, so the other number which you need to know is that we're producing 40 billion tons of CO2 per year right now. And so in a few decades, we would use up the next. And a few decades after that, the next after that, degrees Celsius. And the other thing is, and I make a point of this is not exotic consumption in private jets or in some other way, something has nothing to do with us. This is ordinary activity of people in a modern civilization with today's appetites in all senses of that word. Ordinary things including eating hamburgers, commuting to work, building with concrete, going skiing. Each of those has a different storyline related to our being consuming human beings. So here's an image of the 2 degree and the 3 degree world. The 2 degree world is symmetric around today. The fossil energy era is something like that left triangle on in the lower triangle. It took about 80 years of drawing a very crude line through a bunch of data. And we have to go down the other side at about the same pace. One of the ways of talking about the 2 degree future is that mid-century, the fossil fuel emissions will be about half what they are today. So that's 40 years out there, it goes halfway down. So it's not a bad picture of a 2 degree world, it's highly idealized. If you give yourselves 1 extra degree, you slot in a rectangle 40 years by 40 billion tons a year, it uses up your 1,600, you get a 40-year reprieve on the project. It is slower, it still represents determined action, and I put these little yellow arrows on to align with the current slope, and to say if we do nothing, we're on those yellow arrows. I looked up the slope against the last few. We're going actually a little faster than the yellow arrow right now, upward in emissions. And I want to emphasize, we wouldn't be talking about any of this if there weren't a climate problem. We would have, probably, happily have a fossil fuel era that would last several centuries. The buried hydrocarbon is there. It's cheaper than a lot and convenient. It's got these amazing energy densities. And one of the things that occurred to me as I was putting this together is how nearly were we, if we knew nothing about climate change and the CO2 absorption in the atmosphere, and it was 2018, we just had missed this piece of science, which is, it's not so hard to run a scene, run a film where nobody goes up to Mauna Loa and measures the CO2 concentration. Nobody goes and does the ice cores in Antarctica. And a few other things that really have made us quite convinced that we know a linkage. And we just had the observational information about what's happening today. The ice in the Arctic is melting. Floating ice is melting. Storms are getting stronger. Would we have concluded that that something other than natural variation was actually responsible? Are we already at a point where we couldn't have walked away from that assumption? I think we're not there yet. It's an interesting thing to think about. What would have wakened us up to the fact that we were doing something that was harming ourselves if we didn't have the science? To the extent that the answer is it might have taken even longer, we realize we have a debt to the climate scientists. And we ought to be pretty interested in how vigorous our climate science is today, how many satellites we're putting up, what the total budget is for climate science, how many ocean monitors, how many stations in Antarctica. And I think we have a way underdeveloped climate science program globally compared to what is matched to the solutions we're talking about trying to accomplish. So this budget idea is a really nasty, important idea. The carbon budget, how much can we emit forever? It's out there. People have absorbed it as a starting point of a conversation. It doesn't matter whether it comes out in 2060 or 2020 in this limit. It doesn't matter whether it comes out of Arab oil or it comes out of Chinese coal. It doesn't matter whether it goes and solves a poverty problem in an Indian town, or it drives a Mercedes on an Autobahn. And the only thing that I think one can add from the science, with the science background, is when I'm taking the carbon out, I'm also taking out hydrogen. And things being equal, I'd rather take out as much hydrogen as I can with the carbon, because the hydrogen, when I burn it, goes to water, the carbon goes to CO2. I get energy from both. The more I can get the energy from the hydrogen, the better. Now, natural gas is CH4, coal is about CH, or even CH.8, and so they would seem to tilt toward natural gas. That translates, of course, in the carbon price to the fact that natural gas is advantaged relative to coal if there's a carbon price for exactly the same reason. The other thing one must add is that CH4 in particular itself is a greenhouse gas. So if you leak it in the process, you can undo the advantage that's represented here. I can get back to that with questions. So those are my part of the context. Other part of the context, how am I doing on time? Not terrifically. When do we have to stop?
We have till 5.
Okay, so then I can take another 15 minutes, I'll be done.
Although hopefully you'll have time for questions.
Yeah, 15 minutes, just 20 minutes for questions. Okay, so the other part of the story of the context is that the shift in the importance of the developing world versus the developed world has happened in the last couple of decades. And it is really the case that, I'll say that short in a minute, that the developing world's patterns of industrialization matter more than anything else toward the amount of emissions. These budgets, the amount of emissions we're going to have. And secondarily, the developing world is not choosing patterns of industrialization, for the most part, that are low carbon at this time. The industrialization is going on the backs of coal, and we're not paying much attention. So again, in terms of what is carbon dioxide removal distracting us from? It's distracting us from really bearing down on what various communities can contribute toward finding a new path for industrialization relative to the one we follow. So with Steve Davis, I did a calculation. We have a paper out in Environmental Research Letters where we introduced the idea of committed emissions. At the left there, you have this a stack of squares vertically and horizontally. This is some, let's say, power plant. You build it in the beginning, and today's accounting, you count the emissions every year that they happen, so you have a horizontal bar of emissions. An alternative would you count them at the moment that you put it online. You say this plant is going to run a certain number of years, and so by building it and putting it online, we are committing ourselves to all those emissions, and let's count them right now. Sort of, it's some of the spirit of a mortgage versus a purchase. So when you do that, actually Steve Davis was part of a team of 3 people, Ken Caldera and a guy named Matthews, that said right now, if we stopped producing anything, building anything that used fossil fuels, but let things run their natural life, how much emissions would still result? They made an assumption that a power plant would last 40 years. If it was 25 years old, it would run 15 more years, but there'd be no new ones. I looked at that paper and I'd had an idea from some time before that that was an important number to understand in historical terms. How were we doing compared to in the past for the committed emissions at a given in place? So Steve was able to go back to that same database and say, if I did that calculation in 1980, 1981, 1982, and so the left, this slide shows a particular year's story where the total emissions committed we're at 2012, looking back, everything built in 1980 is either fully gone, in which case it's all in the black area. The picture below line is the mirror image of the one on top, but the one on bottom separates what's already happened from what's still left to happen. And so you see that let's say 1990, there's about 9 billion tons of CO2 would be emitted by the power plants that were built then before they ended their lives, and about half of that is already emitted and half of it is left to go. So you add up, and the one you're interested in is the remaining commitments. The remaining commitments go down if you don't build anything more. In the world, they've been going steadily up, the remaining emissions. They're about 300 billion tons of CO2 in 2012. And my collaborators, I went back to them and said, can we update this to 2016? And I'm not sure I can, they're still redoing it to make sure there's a consistent database. But it looks like it's continuing to rise, which means we are building more coal plants every year in the world than we are, and gas plants, than we are retiring. The one on the left is parts of the world, the one on the right is fuels for the same accounting. So we are not even turning the corner in terms of the commitments we're making to the future. They're getting bigger and bigger every year. I was using a baseball analogy before. Have we turned third base and we're heading for home, or are we trying to get to first base and beat out a single? So much depends on that. Committed emissions show up in the building sector, again, especially in the developing world. This is just a picture I saw and said, well, that does it, but you could get thousands of alternatives. Sprouting mushrooms of multi-family homes by how many people do you think live in that complex? Maybe 10,000. How are they built? Are they really incorporating everything we know about low energy construction? What kinds of appliances are in there? It's not as bad as it could be, but my impression is that in general, the patterns of development of a building complex like that would happen in the US and in China and in many other countries, developing countries, are about the same. They're driven by first costs. Standards are not that strong. They're not that well inspected. They're not that well designed. There's not a lot of priority. John and I go back to our buildings days. These are the kinds of, John actually worked in an apartment building nowhere near as big as this one to understand energy efficiency. And there were stories of these sorts. How well understood, the operator of that case of the boiler, as I remember, was not at all educated in what he was doing. And on and on. The key concept is leapfrogging. I made this slide for a talk in China when I decided I couldn't count on the translator to be able to translate the word leapfrogging, so I better show a picture. And this is about what isn't yet happening to anywhere near the extent that it would need to if we were really dealing with climate change in earnest, which is, there are stories, and I think I've got one there. China is building high voltage transmission lines, AC and DC, beyond anything we've done. They're not asking how, they don't mind being first. These are important technologies. And so they're leapfrogging in the transmission area. But in many other areas, their cities are being laid out, car-based transportation systems and so forth, that are making it very likely that we aren't going to see this 2-degree world. And I worry neither nor the 3-degree world, because this kind of thing is we just as soon not know, don't ask, don't tell, and so forth. If you look at the individual level, I want to make a related point. I was involved with another paper. These are the 2 papers I'm quite proud of. The lead author was Shoibal Chakravarti, who was a postdoc with us, physicist, now in Bangalore, and Massimo Tavoni, who is, I believe, an economist, who is also working with us, is in Milan. And we asked the question, suppose you could forget countries and just take all the people on the planet and estimate their emissions in such a way that you weren't double counting, and everybody's emissions added together was the global emissions. You did that by looking at income distributions in countries. You then looked at the country just long enough to see how carbon intensive the country system was. Would have a higher multiplier, a lower multiplier for Norway, say, than for Poland, two extremes in carbon intensity. And then you discover there's then you bin the emissions. And we took as separate binning levels 10 and 2 billion tons of CO2 a year. US being 20, heading down toward 15. 1 billion people, roughly, are in the top category. And they account for 3/4 of the total emissions. 25 out of some number, maybe 60%. The poor people, in the billions, emit hardly any CO2. And if you gave fossil energy to the poorest people to get them off into the bottom level of consumption of fossil fuels, a diesel engine in a village, a bike, a motorbike, some kind of LPG stove, that emissions would not add up to more than a 10% effect on global emissions. The poverty agenda is not in the way if you think in terms of individuals. If you let India say we're a poor country, we need to raise our level by a certain percent, then you get big numbers. But the poverty agenda, which is often mixed in with this, we've got so many poor people, we'll never be able to keep the carbon emissions down. It's not the right way to frame this. It's emissions of middle-class consumption by things we all do every day. That is getting spread around the world because we have a single view of the good life. And this is just one more way of saying it. Papers alluded to, so I want to talk now about supply technologies, low-carbon technologies in general. How many of you actually know this reference to stabilization wedges? I'm curious. Most of you. So I hit a home run with Steve Bacala when we swung the bat together. And our view of low-carbon options was, I think, captured by this picture. I just put this slide together. Very risky. People asked me to go back to the stabilization wedges. I didn't want to. I want to be a one-paper guy. But this is important. We are agnostic about a variety of options to lower carbon emissions. So an image of that is just out of the starting gates. No one knows which horse is going to win. And they're running side by side. 2018, they're spread out. There is quite a bit spread out. Still running. So who's in front? Which options for low carbon, what strategies would you put in the front? I want to hear words from vocal, audible words.
Coal to gas. Fuel switching.
Coal to gas is in front. Anybody else?
Solar and wind.
Solar and wind? I agree with the solar and wind guy, but they're out in front. But you'll see in a moment that I haven't got coal to gas very far behind. Who's way in the back? I got into an argument with someone about this. Is all our hydrogen for fuels. In 24, is I think the same year that President Bush announced that the child born today will drive a hydrogen car. I had a colleague, Bob Williams, who with his colleagues had really been pressing the hydrogen economy. Prius had not arrived in the showrooms of America, I think, till a year or two later. It was already marketed to some extent. There was a huge pessimism, driven a lot by things that happened in this state about batteries for cars. We're working forever on them. They seem to have nothing much to contribute. I think I have the word sodium sulfur in my head. So we had a sense that to have a zero carbon distributed energy system was critical, and it couldn't be done by electricity, so it better be done by hydrogen. I think it has faded. We had gas for coal. No, we had, CCS and nuclear pretty far back compared to where we thought they would be. We thought they would be more competitive, and they turned out to be so far. Why gas and why was wind and solar doing so much better than CCS and nuclear? I can think of two major reasons. wind, but especially solar, are modular. So you have lots and lots of units and therefore lots of opportunity to learn. CCS and nuclear come in big chunks. And the second is there was a political opposition for related reasons to CCS, put it underground wherever you want, where it was tried to be put underground. Nuclear had lots of public opposition, which translates into costs. But anyway, that's what's happened so far. Are those other guys, CCS and nuclear, out of the race? I'm not so sure. They've got to keep them in mind, but they're the phenomenon of the past 14 years is the phenomenal growth of solar and wind. There's 100 times more solar capacity on the planet than there was when we wrote the Wedges paper. Roughly 3 gigawatts has gone to 300. There's 15 times more wind, roughly 40 gigawatts has gone to 500. So that's maybe really so important that it's the most important thing that happened in the last 14 years because it presents a vision of a swap of today's fossil energy system for a wind and solar-based fossil energy system. Alongside two other visions, both represented by the CCS and nuclear, a world where we stayed with fossil energy, but we've separated this emission, the energy generation from the emission, and didn't get to the atmosphere. Not ruled out, certainly alive in my mind in 2004. And the nuclear one, which goes back in my case to graduate school, where we were going to run the world on nuclear energy, was just in my lifetime. I would argue that the solar and wind system is more different than the other two. Therefore, the adjustment is going to be more complicated, deserving more attention, more original ideas about how we handle especially the intermittency of solar and wind, whether we will have to adjust lifestyles more because of that. I added gas for coal. I add way up in front, and even more efficient coal plants, because the coal plants that are being built in Asia, big time, are more efficient than they were in 2004. There's the word ultra supercritical. You can add more adjectives in front of ultra and keep going. The end-use efficiency has always been there, but not that prominent. Biological has also been there. Carbon, we talked about some of that before. And storage, which was not on our initial list, we call it the dark horse, but there were more than 15 at the beginning, if you counted them up at that horse race, is coming along quite strongly as well. Is it already time to declare a winner? I've said all those words. It's a hard question. Every solution is dangerous. All of these can be done wrong. And I'm a worry bird. I'm temperamentally a person who doesn't believe in good news. It's not the most pleasant person to be around. When I hear nuclear power, I think of diversion of nuclear materials into wars. I was in China not too long ago, about a year and a half. Actually, I was there when Trump was elected. And I sat next to I was placed at a lunch next to somebody who's very prominent in Chinese negotiations in the climate world. I asked him about nuclear power. I said, China's counting on meeting its low carbon objectives with nuclear power, right? He said, of course. And I said, China will also be an exporter of nuclear power? He said, of course. I said, to what countries, for example? He said, to Saudi Arabia. I said, what does Saudi Arabia need nuclear power for? He said, for its climate change objectives. So we have, if you like, a cover. And if I had to guess on the world's most dangerous place for a future, for nuclear war in the time frame of the younger people in the room, it would be Iran and Saudi Arabia. I don't want that I don't want to see that. So my overall point, if everything is dangerous, it's essential to add conditionality to every option, to say, well, let this go forward provided, and in the nuclear case, provided might be, we really have got a strong anti-weapons, nuclear weapons regime, with lots of global inspections, lots of compromises of sovereignty, like those in Iran right now. That includes ourselves. Our civilian nuclear sector is internationalized in some way. And that more generally, I talk about two-sided reasoning. It weighs both the threat and the solutions. And I've asked people in the climate world, can you imagine getting to 2 degrees and regretting how you got there? So I'll ask you all. The world is accepting the 2-degree scenario. Let's save that for discussion, but I have had, as a field report, I've asked people prominent in the climate world, and they say, no, I can't imagine getting to 2 degrees and regretting how we got there. And I think that's a failure of imagination. I worry very much that kind of framing is in place. I mentioned conditionality for nuclear power. Let me mention conditionality for biocarbon by way of this illustration. I'm almost done. What will go wrong if we move headlong to maximize global biocarbon stocks without conditionalities? So this is an assignment for SEAS. Suppose you're a forester or an agronomist in a world where the carbon price was very high, and your single objective that your bonus is going to depend upon is that you put as much carbon away as possible in choice of crops and choice of management. Be inventive. Do everything you can to get your biggest bonus. Now, change roles. You're a policymaker, knowing that that is what the forester or agronomist is out to do. And what conditionalities would you place on that market so that he or she is doing things that you want to see happen, not those that don't? Obviously, the optimization in the first part of the problem is within a set of rules. What are those rules? Anticipate them. That some approximation to that happens already, but that's what I mean by adding conditionality, so that what results is not worse than not trying in the first place. Yeah. So a favorite framing of the Hippocratic Oath for me is, I will apply for the benefit of the sick all measures that are required, avoiding those twin traps of overtreatment and therapeutic nihilism. To me, I think all of us who are in the older generations have been in a situation where either ourselves or somebody close to us has confronted a very serious disease and some very strong medicines that might help. And when you're in that situation, it's truly difficult. You're making a judgment call. You and a doctor and perhaps the individual in mind, and that's the world we're really in. But the choices, the drugs to solve the climate problem are strong. Their side effects are real. The problem is serious. That's that bottom right quadrant. And I would say, and this is not usually said, the lowest conceivable greenhouse targets, achievable only by casting caution to the winds, are not optimal. We have to do this two-sided reason. So that's the context in which I think about where we are right now. Thank you very much. Q&A. John, you want the first shot?
I'll leave it to others.
Well, I'll rush in. Continuing with your horse analogy, I wonder, is not the horse already out of the barn in terms of nuclear? And what do you think is the future for modular nuclear reactors?
My second answer is, I don't think modular changes very much. Maybe they bring down the costs a little bit. They offer the opportunity to develop a new reactor, say for example one safer, intrinsically safe. We haven't used that opportunity. We've used it to build what we already know. So DOE had a competition for open to all concepts. They looked at some exotic ones and some that were based on the pressurized water reactor, and they funded the pressurized water reactor. Most of them have fuel cycles. They're as big as 300 megawatts when they're still called small. They have fuel cycles, and they have the issues of the nuclear power from the weapons perspective are about the fuel cycle. I don't think they changed the game. Is the genie out of the bottle? And that's been said for 50 years. I don't think people would have imagined that you could have a regime like what has been accepted by Iran to separate a nuclear power program from a nuclear weapons program. That's a lot of intrusion, but it sets a bar for what you have to do in countries like UAE, where it's been discussed, right, Saudi Arabia, but it'll be anywhere in the world, including ourselves, the amount of limitation of independent national programs. so that there really can be a nuclear power program that doesn't leak into nuclear weapons. In that sense, I don't think the genie is out of the bottle. We've proven it's not going to be welcomed by the nuclear industry. But if we really took climate change seriously and said we don't want to see a nuclear war being a leak out of this climate regime, we would do something like that. I mean, I'm trying to remember the usual the genie's out of the bottle is said by the nuclear people a lot. Meaning, I think we already have weapons, we already have power, don't think you can break the connection between them. I forget sort of how that argument, it's like not remembering a chess opening. There's 3 or 4 steps that follow from that. But the bottom line is, I think we can still do a lot. If we're gonna go down the nuclear power road, there is a lot we must do to keep the world from having a nuclear war. Or several. Yeah.
In one of your slides, you had a reference to what if we never recognized the link between carbon and climate? Isn't that essentially the business as usual scenario?
No, I don't think so. Oh, this is not gonna work. Okay, I gotta get back to it. Anyway,
Well,
let me not even try.
It was basically just saying, what if we never recognized the link? And business as usual seems to be just not recognizing the link.
I think that was your little matrix,
No,
right?
Pardon?
That was a little matrix that had the 5-degree world in it.
The philosophers would not agree with you. I mean, the issue is whether intention matters. If you don't act because you don't know, it is different from not acting when you do know.
Well, of course, that's true, but the net outcome is the same.
Outcome is the same, the moral argument is different. Yeah. One, two, three, Gordy.
Okay, comment on your matrix. I'm in the lower left corner for 3 reasons. One is California, which has done it. The second is that countries like China have started to require to reduce pollution and to get carbon goals. They've started to make requirements on buildings and everything. They've just begun, but they've started. And the third is that the people who brought us smartphones and SpaceX and such things are getting into these things, and they've actually made things happen. So I'm in the lower left corner.
I hope you're right. And there certainly is more reason for hope than when I first put that graph together. It was in California that this inequality sign appeared. S is less than C. Capital S is less than capital C. Solar will be cheaper than coal all by itself. Similar to the argument made in nuclear in our days.
And it's working.
It may work.
There.
I mean, right now, if it works, there will be developing countries which bypass the fossil energy era.
Yeah.
Two.
You had a slide that said that there's enough fossil fuel to last several hundred years, I think, and what's the evidence for that, and how does that break down between the different fuels?
Well, it's a geologist's question. There are certain, I was influenced by a guy named Arnold Grubler, who wrote papers, he's at IASA, which tried to really put numbers and end up with multi-100-year fossil era. There was this, I had a colleague at Princeton named Ken DeFaze, who was one of the people popularizing the opposite view, that we had that we were halfway through our fossil energy supply.
He was talking more about oil, I think, wasn't he?
He was talking specifically about oil. It was generalized to be everything. There was this phrase, unconventional versus conventional, which is a boundary that moves, because what's after shale was unconventional, is now the primary source of both oil and gas. There's a huge category. There's a lot of the history of the planet has left us with a large amount of reduced hydrocarbon in rocks and in ice even. That, when you add it up with geologists' estimates, is hundreds of times 40 billion tons of CO2 a year, which is 10 billion tons of carbon a year. So billions of tons of reduced carbon. There's a whole category called methane clathrates. Clathrate means ice hydrates. It's reduced methane. It's methane in ice pockets, in an ice volume. Incredible quantities. They are already of interest to industry. They can go after it. Maybe they will worry about runaways, but if you get at it safely, bring it into the world natural gas market. Oil and gas, I mean, the shale revolution kind of undermined the peak oil view of the world, because this was a category that was not being included. And it meant, yes, these symmetric bell-type curves or logistic curves might be right for a particular kind of resource. When you go through it and you reach a certain point, it gets harder to get. But if there were new kinds of resources, then that was going to be one bell curve after another after another. So I think the wishful thinking behind the peak oil and its generalization, all fossil fuels, was an example of how much we want to believe that things are simpler. I didn't believe it at the time, because I've been influenced by a couple of these papers that showed when you really go back to the rocks and make estimates, they're enormous. They're not factor 2 right, but they're enormous. Yeah.
Marvelous talk, and I wholeheartedly agree with your point that we should curb our enthusiasm somewhat for direct air capture while there's still concentrated emissions from power plants and boilers of buildings and vehicle engines as well, as we were talking about before your talk. To go to your Kentucky Derby analogy, you mentioned modularity of wind and solar as a reason why they're leading the pack.
Especially solar.
CCS is trailing behind. I wanted to see if you would agree that the tax credits for wind and solar that until recently CCS did not enjoy, maybe also account for that
Yeah,
differentiation.
all over the world, solar was substantially subsidized, bigger in many countries than in the U.S. at its peak, Germany and Japan included.
Right. In the budget, which was just passed and Trump signed into law, I don't know if he knows he signed this, but there's now a $50 credit for CCS for storage.
I started turning that into what would be my probability estimate of whether he knew it.
Though he digs coal, so he might actually be in favor of this because it could have
Yeah,
been.
but
But I wanted the people in the bottom left of your quadrant diagram, I think there's been some opposition to CCS as being a crutch for continued fossil fuel use. And
Yeah,
now that we have these credits, I'm wondering if we're starting to move beyond that thinking and admitting
there are a
this
lot
is-
of interesting questions where it may really be, matter a lot, which bottom left versus bottom right, how you come out. So your example is a good one. There's something called Q45 tax credits. You've heard that here. It's a data point that, how many of the people in this room have heard of them? A few, but very few. The environmental movement did not send out newsletters in February saying, boy, have we had a big win. A major opportunity to save carbon has become federal law. It resulted from an unanticipated comity between the Democrats and the Republicans, getting substantial numbers of votes from both sides. It was one of the things that's crept into the tax bill at the last minute. And boy, are we proud of ourselves. No such news. It is a subsidy for carbon dioxide capture and storage, which is a part of the air capture story. So if you're an air capture fan, you should be having a little champagne for dinner. It has these amazingly high numbers. The way it was put at lunch, we had a conversation about this. Essentially, the Trump administration has agreed to have as a working price of carbon, basically in the range, but maybe a little higher than what Obama considered the social cost of carbon. $35 a ton of CO2 if it goes into enhanced oil recovery, $50 a ton of CO2 if the CO2 goes into an aquifer and does not produce oil. The difference being someone's estimate of how much the CO2 provider would get from the oil company, because the oil company wanted the CO2. Maybe $15 would be what they get, so we're trying to keep it neutral. So this is in place. It's not capped in quantity, which is extraordinary. Most times you get a subsidy, they say, but we don't want to break the bank, so the maximum we're going to spend on this is X. There's no such X. And it's got a few other interesting elements, including that it applies to carbon capture and use. I'm concerned that people not underestimate the responsibility now to do it right, to anticipate the games people are going to play to get their project credited, and to confront some conceptually difficult questions, like if it is put underground, not underground, put into a product, CC, carbon capture and use, how long does that product have to keep the CO2 out of the atmosphere to credit, to qualify as deserving the credit? These are gonna be big bucks written by the government to people who do certain projects, and denied to people who do other projects. That encourages lawyers. And how will it play out? I think some of us better pay attention to how it's implemented, so we don't have it look like, boy, did that scam, how did that scam ever happen, and things like that. You agree with me, from what I can tell, yeah.
So you mentioned a bit about how we're kind of depending on developing countries to bypass like fossil fuels and coal as a way of industrializing. But I guess how fair is that for us as an already developed and strong fossil fuel country to put that onto developing countries? And I guess also more like wind energy and solar energy aren't necessarily like the most, so they're the most sustainable, but they're not necessarily the most inexpensive ways of
For
getting
now,
energy.
they're coming down, but let's say they're more expensive. So let me
Yeah.
buy your argument, the fossil energy development path is cheaper. Who are we to tell them to do this?
I guess
Is that your question?
a little bit, but also like I feel like that is putting a disproportionate amount of responsibility onto developing countries, like for this issue.
And
Or, like,
therefore, what is your way around that?
I guess that's like what I was asking.
I'm asking you.
Okay.
I'm afraid my conclusion is the world is not fair.
Well, yeah.
And it cannot be fair in this instance. We used up a lot of the headroom in the atmosphere, industrializing. By the time the developing countries got around to it, which was partly our fault that they didn't get around to it sooner, we had something called colonies, it had been used up. Very unfair. But it really comes down to, are we cleaning up what we producing climate change just for ourselves? Or do we believe that the world as a whole will suffer from climate change? And therefore, fair or unfair, the developing countries, to protect themselves from climate change, need to do something far more than they would have had to do if the world had stayed more equal through the 19th and 20th centuries. Which comes down to, is climate change going to be judged to be a serious issue in the developing countries, looking at the problem for themselves? Which is why, I don't know if the slide was in front here, but the developing countries are going to determine what kind of planet we live on. If they emit CO2 at a peak, it's a different kind of peak from the one we were talking about before. If they emit it out of peak, out of resentment, we will have lots of sea level rise, lots of melting glaciers and so on. And the developing countries say, we don't care, this is not a priority, then we'll have a lot of climate change. Because I don't think they'll listen to us, I think they'll make their own decisions.
Mhm.
What we can do is help develop options, teach whatever we know. The Lawrence Berkeley Lab trained the Chinese in their equivalent of their EPA about appliance standards, and they have a better refrigerator than they would have otherwise, because there was some technology to transfer. John, you may know more about that than I do, but it was a pretty exciting story. Whole groups of people from China working in the Lawrence Berkeley Lab, learning about appliance, the details of how you qualify a refrigerator to be a lower efficiency, high efficiency refrigerator. There are opportunities like that. A lot's going the other direction. This coal-intensive development is being done in part financed by developing country banks, and our attempt to control that by only giving loans if they were low carbon has had an end run done to it.
At coasts, the developing countries have a lot of coasts where the water's rising.
Well, we all have coasts.
But they needed help because of that.
Yeah.
Because so many of them live there.
So our assumption, I think you cannot have hope in this problem if you think that this resentment will dominate for the next 50 years and there will not be initiatives to be low carbon. I think the story of Paris is the Chinese actually are concerned about the impacts of climate change on themselves, as well as the opportunities for world leadership, which pay off in other ways. And they are taking this problem very seriously. The good news about the Paris Agreement, when we pulled out, the rest of the world said bye. They could have said, well, if you're not on, we're not on either. Yeah.
You know, the problems associated with having carbon and gaseous form like CO2 and then sequestering it, have you seen any work that might put a limit on how much CO2 could be sequestered geologically?
Yeah, there's quite a bit of work for 20 years in the various international reports on storage capacity for CO2. My answer is it's like any other resource. Pore space is like copper. If you say how much copper is there in the planet, that's not a good question. If you say how much copper is there that could be produced on this planet at this time with these technology and at the price that we have, and then there is an answer. And with the level of exploration we've done at this moment. And then the rest of the answer is that number's going to go up if the becomes more scarce out of a combination of new technologies, new exploration, and a higher price. So the answer how much storage capacity is altogether is how much of this resource called pore space is there at a given time. If you say, is there any absolute constraint that you can pose on this whole story? There is a certain amount of copper on the planet, which is the crustal abundance times the rock or something like that. That's a bigger, higher number, very big number. There's a lot of pore space. It's all of this, underneath us is either sedimentary rock, which is pore space, or it doesn't have any, it's a word, impermeable rock. And many of you know better than I. And if you just look at all the pore space, there are places where there's very little. They're not good places. India is not a terrific place to put CO2 underground, as I understand it, because of its underlying geology of volcanic rock. But as a planet, there's lots and lots. That's what these reports say over and over again. Again, if you don't like if you don't like, each one of these is part of a storyline or a chess game, right? If you don't like CCS, you trot out. There's not enough capacity anymore. Not that nothing new is under the sun, but some of these stories are by now well worn. Yes?
You don't mind me asking a second question? You showed if you run the play in reverse with carbon dioxide removal by direct air capture, that in addition to it coming out of the air, the ocean compartment would also
It'll
be
degas.
involved.
It'll degas some.
Because my understanding was that there's a non-equilibrium situation
It
where
is.
it's still plowing into the ocean over a period of many decades to come, and so maybe it wouldn't necessarily immediately reverse
Well,
course, but could
It'll
continue
keep
to.
going into the question is, at the surface, there's equilibrium between the ocean, dissolved CO2 and the atmospheric CO2. So if in a given moment you take CO2 out of the air, there will be outgassing, if that were the whole system. One set of slides I skipped. Any of you interested in fluid mechanics in this room? I mean, there's a lot of scientists that like to find problems for grad students to work on. In the air capture story, there is a interesting question. Imagine one of our 30-kilometer walls, and we're going to run CO2 through it with a bunch of fans, and on the other side there's going to be 200 parts per million. Now instead, say I don't want to use that. I don't want to do this in a linear array. I want to put these segments of wall, one behind the other. And the second one will see the air that came out of the first one. If I put it right up close, it'll see 200 parts per million. If I put it 200 miles away, it'll see 400 parts per million. Now let me change the distance between and ask how far apart do they have to be to get most of the air replenished from CO2, from normal air that's above it or sideways or some, mostly going to be above it. What kind of replenishment is there in the atmosphere? That is a really interesting science question. It's not unlike the one about how far behind a windmill you have to put the next windmill before you have the momentum of the air restored. One is a mass, one is a momentum story. They are probably kind of isomorphic. I love finding these little science ideas because smart people can solve them. I can put them in place, and then we learn something.
Somebody asked something. I want to go back to the committed emissions
Yep.
issue, and you nicely showed a big Chinese apartment complex and raised the questions, regarding how well it was built and, the quality of and efficiency of the appliances and all of those things. So behind a certain part of committed emissions, which is going to be whatever it is, whether it's a coal plant or wind or whatever, on the supply side, there's also committed energy demand that is due to these infrastructures. And
Yep.
the built, buildings infrastructure is a huge
Yep.
part of that. Kind of based on, this was some of your own earliest experiences, you alluded some of mine, buildings energy efficiency, all the hard work, empirical work and learning there. What's your take on how well we can address committed energy demand? In this case, it's going to drive a big chunk of committed emissions through efficiency, given how much knowledge we've gained, but again, the experience in terms of deploying that knowledge.
Conceding that, is that the rest of your sentence? Yeah. I mean,
Yeah.
what you're bringing to my mind is images of concentric circles. Yeah, the inner concentric circle is pure technology. What is actually in that building in the way of a furnace, light bulbs, how well insulated are the walls, what kind of windows. Then is the support industries that are making light bulbs. Then the behavior which decides on what kind of lighting we want. Then what kind of apartment building does someone want to live in the first place? How big do they want it to be? One of the things I think is pent up in the developing world is people in those apartment buildings, those are small apartments. Maybe 80 square meters, 800 square feet, just a guess, it's a working number. And these are people who are living, this may not be this may be a higher, but many of these are in new cities, and people are actually in their first apartment. They came off the farms. After a while, that's not going to be the apartment they want to live in. So the committed commitment is to an apartment, not to an 80 square meter apartment. So there's the next generation of apartment buildings. The modern lifestyle with appliances and light at night and places to go and all of this is apparently irresistible. There are 7.5 billion of us. How are we going? I mean, I think this problem is immensely difficult. And when I find people ready to celebrate, I'm the skunk at the party because, this is we're just beginning to get our arms around it. That's this first base, third base, conditional emission, conditionality, all these things. I think I went right past the slide about geoengineering, or dropped it out by mistake. There's another way of thinking about this problem, which we absolutely must solve it. We'll get really nasty messages from the planet about how fast the sea level is going to come. We will not have strong enough solutions in our usual list. And there is increasing interest in saying the planet is actually a managed system at the planetary level, and we can change the amount of incident sunlight by putting up some shields. And it takes only about a 1% change. Well, we've got 31%, or some people say 30% of CO2, of sunlight from the sun is reflected before it ever becomes heat. And so it doesn't have to get radiated away in the infrared. It's reflected away in the visible and near infrared. So just increase that, and we'll compensate for any warming from the gases. And that's called solar radiation management. I did show that one picture, but didn't elaborate this in terms of conditionality. Many people think we have to have public discussion of this option beyond anything we've seen so far. It's already pretty well lubricated in the technical community. But again, it's how close to where we work is it actually something they've never heard of. If you go to the engineering school, go to the electrical engineering department, maybe they've never heard of it. How many of you have not heard the word geoengineering and the idea of managing solar? Probably nobody here. But how many people think that if they went next door to their neighbor or talked to their sister, they would have heard of it already? I think it's still, as you said, for the cognoscenti. But not for long. Religious leaders are gonna weigh in. People are gonna be really wanting help. And that's another part of this context. CDR does not help this conversation, I don't think, because of the argument about pace. If that's the argument we end up having, I don't know exactly where it takes us. It certainly takes us to how much change do we want to take over the planet, or accept that God intended some level of suffering for us? I mean, maybe that kind of conversation we actually have.
Let's thank Rob and a little and chat informally as long as he can
I'm
make
getting,
it and before you drag him off.
I'm so pleased to have an opportunity to talk to you all.